Good morning, everyone. Glad to meet you. I'm John Lauletta. I'm the founder and CEO of Exactor. We've been in business for 14 years, and for the last 6 years, we've been working with the universities in Ohio and have created a number of teams. And I'd like to share first why we're doing our student teams, what we're getting from that, and then I want to share two projects which have just recently come to a commercialization point, which is quite exciting. And the students that have been involved in it, some of them are getting jobs within those commercialization opportunities. So we'll just move right ahead. So, why we're doing student teams, there's really two sides to this equation. For us, for industry, we're getting new ideas and new approaches to problem solving. The students bring, I think, both a unique set of tools with them, but also a very can-do attitude. And that's been a real plus for us as we're trying to solve some really big problems in industry. And when you're working at a company for a long period of time or in an industry, it's really easy to get closeted with your thinking. And when someone comes and challenges that thinking from a university, it can be really quite exciting. The other thing is we get access through the students to academic conferences and networking opportunities, which is a real great thing for us. So a lot of our students have written technical papers on the work they've done for us, and we support them as they go off into the world to present those papers. And we're meeting a whole new group of people that we would never have had access to in the past. From the student side, there is an industry experience, and I think that's kind of a shocker to some of our participants when they first have the new set of guidelines and responsibilities that are put on people by industry, because it is a different pace, a different rate at which things are done, and the completion of it doesn't just hurt the student. If a student doesn't complete something for their class, their grade suffers. But if they don't complete something for a project, the project suffers. So it's a new kind of paradigm for some of our people. Other people, though, with the universities and the teaming efforts they do today, they have had that experience already. Certainly, the research that the guys are doing for us and the ladies in our programs often becomes part of their research for their graduation. So that's a great thing. They get something they get to work on with industrial impact, as well as get that work done for their research programs or thesis or dissertations. So a little bit about Exactor, just a few words. We're focused at the electric utility industry. We help electric utilities improve the performance of their grid by evaluating the condition of electrical equipment. And we do that in a variety of ways. I'm going to show you two projects that we worked on with universities that address two very unique and different problems using two unique and different sets of technologies. So we'll get into that just a little bit. But Exactor, like I said, I think earlier, we've been in business for 14 years, and we've worked with electric utilities throughout that period. So we're well grounded in what we do, and we took our technologies to the universities, and we developed new methods. We licensed new technologies from the universities we're working with. We've combined all these technologies into some very unique solutions for the electric utility industry. And we believe we've created a lot of jobs for our student team members. So here's the people we work with in Ohio. You recognize all these universities. You may not recognize Bright Energy Innovators. They're an incubator in Warren, Ohio. And one of our students from Youngstown State is actually opening an office at the Bright incubator as part of one of our projects that's being deployed in Akron, Ohio. And I'll explain that to you in a few moments. So we're actually, we've created a potential company out of the work that we're doing with students, if the student would like to continue that work after the incubator sets up his company. And it's basically a maintenance depot for a deployed sensor project in Akron, which is very exciting. And we're actually just finishing the deployment of the sensors, and which I'll explain to you in a moment. And on next Thursday, we'll be finishing the deployment, where we're installing sensors on garbage trucks in Akron, Ohio, to monitor the condition of the electric grid as they drive around the entire city every week. And we're using that to drive an AI program, which is quite exciting. So here's some tangible accomplishments from the work that we've done. The first is we've had a 6-year program. I think that's tremendous, and we've gotten some great opportunities to work with professors, universities, outreach programs, the Bright Innovation, Energy Innovation Incubator, and so on. During that period, our teams and us have brought to the universities $5 million. So that's been a great feather in our cap, and something we're very proud of. And these are from grants that have been awarded to the technology programs that are underway. We've had 3 patents issued. Each of those patents has student names on them. So we're very proud of that, and that's something that those students are taking with them into their careers. We've developed 3 technology programs. These are focused efforts from the technologies that the students have worked on with us to commercialize 3 different products. 2 of them are at an end state right now, ready to go into commercialization. We've had 3 commercial launches where we've actually produced a minimally viable product, an MVP, in 3 different areas that we brought out to industry for that work to move into other people's development. So people are looking at licensing these commercial opportunities and developing products from them. During the period that the 6 years, we've graduated 5 PhDs, and they've used the research that they did with us in their dissertations. There's soon to be 1 more. So that's what I'm most proud of. I think that's something that I'll look back on my career as being part of those people's launch into industry, and I'm just so very proud of that. We've also had 9 master degree students graduate during these 6 years, and we have 2 more that are in their final thesis work right now, and probably will graduate in the fall. And we've developed 2 university license programs. So as we've worked together, the universities have had technologies that they owned from previous work at the university that Exactor has licensed from those universities. So we've created now an opportunity to have a revenue stream back to the universities that we partnered with. So I think it's just been a wonderful win-win all the way around for everybody that's been involved in our programs. So what are those programs? Well, I'm going to just go through 2 of them with you, and we've got actually several that are going on, but these 2 are, I think, kind of exciting, so we'll go into them. There's 2 technologies involved. One technology called active clamp. We'll talk about that first. And the second is an RF partial discharge discrimination signature program that we've developed. So the first program actually works with a real problem in underground electrical networks in downtown areas. These are low voltage networks. They're in the 480 volt range. And the cables split open from age and heat. The cables are simply copper conductors with butyl rubber coating around the outside. And just like an extension cord at your home, if it cracks open, nothing's going to happen unless you step on it or spill something on the crack that might cause a electrical fault. But the same thing happens in downtown areas. And these cables, as they age, crack open. There's no way to test these cables because they're hooked together in a matrix in a true network. So if you test any one of them, you have to disconnect the network to do that, which causes a power outage in a downtown area. Not a good thing. So the cables just simply aren't tested very often, if they are ever tested. And then water and salt get into the conduits from in the springtime after the winter, and all the salt that gets on the roadways and gets washed in there. And now you get a conductive path. And when that conductive path begins to arc, the organic compounds in the butyl rubber can cause explosive gases to be generated. And when they explode, bad things happen. So the cables and the conductors are very difficult to test. Usually the tests are destructive. And these cables have been laying still for 50 to 60 years. And just moving the cables to test them is something that could cause the cables to be damaged. So we brought together 25 utilities who told us, if you want to help us in this area, the test has to be completely non-destructive. It can't require any disconnection of the power cable, and it can't require any power outage of the 60 hertz power being delivered. So these are some of the types of cables that we're testing. Like I said, the one on the right, the lower right, is the type of cable that would be used in an underground low voltage network. The one left of that is a medium voltage overhead cable that might operate anywhere from 4 kV to a 35 kV, and it's called tree wire because it has a rubber coating on it, or some material coating, that prevents trees from touching it and causing a fault. The middle one is a medium voltage concentric neutral cable. And the problem with these cables is that gray insulation layer ages. And when that ages, high leakage currents occur, and that can cause a fault in the cable itself. And then there's overhead conductors on transmission lines that have steel or composite cores in them. And we can apply this same technology, this active clamp technology, to test all of the variety of these different cables. The one we're going to talk about is the one on the right hand lower corner, the low voltage network cable. So when they fall, this is what happens. You get uncontrollable fires that they just have to let burn out. You get launches of the 80-pound manhole covers, and you can see one in that red circle flying away from the ground. As this guy was being interviewed, because he was on a news program, and he was saying, yeah, there's smoke coming out of the street down here, and all of a sudden, boom! You see this cable, this overhead shot of the manhole cover flying up into the air. It came down and went right through a bank window. Luckily, there was nobody inside. And you get these emissions that are noxious. So it's a real bad problem. And this is some of the equipment we found when we did our testing. And you can see how the equipment just is rotting away. And that's just because of the age and the horrible condition that underground networks work in, with all the road salts and chemicals that get in the manholes and so on, and then water and freezing and thawing and all that. All that just starts to deteriorate all the equipment. And you can see it's not a very nice environment. It's a dirty place. So what we did at the University of Akron, we developed what's called active clamp technology. It allows us to connect to a conductor and induce a current flow with an injector into the conductor, and then block that current flow from going further. And this current flow is a high frequency current flow, so it can run right along with the 60 hertz voltage and current without interfering with that. And when we block this signal, the high frequency current bleeds through the insulation to ground, through the shunt capacitance to ground. And with that, we can evaluate the condition of the materials in the insulation. And we've developed the models to do that. This is a block diagram of the injector that the people at or the students at the university developed. So here's the injector, and then a blocker on either side of it, and then in between there is the segment of cable that we're inducing the signal into. So we've met all the requirements, that were given us by the industry. It's a non-destructive test. The voltages and currents are low. They're high frequency, but very low energy, very low voltage, very low current. We don't have to unhook the cable to inject our signal because we use a clamping device, much like a CT, but it's now inducing a current into the cable. And then we block that with the blocking circuit itself, which is kind of like a Bose headphone, like a noise canceling headphone. It listens for our signal, recreates it, inverts it 180 degrees, and re-injects it into the cable. So it's like basically virtually cutting the cable at those 2 points. And that allows, of course, no current flow out, and all the current then flows through the branch, the shunt capacitor branch. It's basic transformer technology that we're doing, and we're solving the transformer equations that we all learn about. It's just that one of the parts of the circuit is earth, and we actually create a circuit of line to earth and returning that current through the shunt capacitor's branch. It's quite exciting and works quite well. This is just some of the equations that go along with it, the state equation for our transformer. So we start with all of our academic programs with the students teaching us what they're going to do and how they're going to do it. And then we go to the laboratory and start working. These are just some of the things that the students came up with on the modeling side of the program. The beauty of working with a university is your modeling tools are so great that we have very high confidence when we move from the laboratory into a product or a subsection of the product that it's going to work, and we can test in a variety of ways while we're still in the laboratory without spending a lot of money on production of materials or putting anyone in danger. Here's the active clamp injecting circuit. It's very simple, really, when you look at it from a block diagram. We're just creating a signal that's induced into the cable itself and controlling that very well, and then measuring the results of that. So we apply a voltage to the circuit, it induces a current into the cable, and we measure that current flow. And the result of that gives us the impedance, the high frequency impedance of the cable itself. So now we can evaluate the shunt capacitance because the current has nowhere else to go but through the capacitive pathway in the cable. This shows how the blocker works, and you can see here is the input, the sine wave. It runs at about 100 kilohertz. That's the induced signal into the cable. And then the right-hand side shows the reduction of that signal or the attenuation of that signal at the blocker point. And you can see within a few milliseconds, it's down 40 dB. So we get a very good cutoff on the signal itself. And that allows the technology to do its work. So the priority was the underground cables that we talked about, the secondary cables, and we did that work there. The great thing is that we met all the requirements. It's non-destructive, it's non-intrusive, we don't have to disconnect anything, and it's non-invasive. The cable remains in service the whole time during the test, which has met all the requirements that the utilities put on us for this technology. Now that we've tested it, we're moving it into commercialization. So we'll start building the hardware that could actually be used to clamp onto a cable and so on. The way it would work in the field is you'd go to two manholes, put the injector in one and a blocker in the other, and then you test the cable between those 2 points. Very simple. Here's our guys at the University of Akron working on cables that were provided by American Electric Power. This is our phase one was the model development. And you see the team there working. Phase two was scaling the model up to an actual cable. And AEP brought us cables that had were new as well as cables that were damaged and old. And so we had the chance to do both. And then the third was when the whole team went out to do a field trial down. We didn't go down in the manholes, but the partner, New River Electric, did for us. And our guys are all there in the yellow vests with their computers in the back of that truck, evaluating the signals and systems that were operating. So it was really quite a wonderful experience for our team. The model development itself had a variety of the students working on it in different areas, led by two professors at the University of Akron. And then when we did our field tests, you can actually see where the cable was. So here's the head end of the cable right below our team. And down, you can see a police car at the other end of the street. That's where the other end of the cable is. So we had our injector here and our blocker installed down there. This is Matt Monroe. He's actually now at Case working on his PhD. And he's teaching the people from New River Electric what they would have to do to apply the technology in the manhole. So we stood above ground, above the manhole, and the New River guys are down under the street here working away, applying the technology. It was really quite an exciting, you can imagine, an exciting day to be part of this project. So that's one of the technologies and one of the projects that we did. The second one is more focused at the electric grid and the operation of the grid. And we've been asked by the Department of Energy, is there a way to evaluate the resilience of the grid? So we always think about the grid from a reliability standpoint. You know, is there an outage? Is something fail and cause an outage? But what about the grid as an organism? And how does the grid react to things like an ice storm or a rainstorm or heavy load periods or season of the year or anything that you could imagine, air contamination? So we developed a technology from Exactor, our patented technology, brought it to the universities, and we developed a new way to evaluate the condition of the electric grid that's never been done before. So in that, we brought in utilities, and we said, to do this, how do we need to develop sensors that we could deploy across the grid in a way that would be non-intrusive to your operation? They said, first, they have to be autonomous. They can't require anybody to get involved with them. They have to be have to turn themselves on, turn themselves off. They have to take care of themselves, because we're not going to take on the responsibility of another network that would need to be operated. They have to have minimum power requirements. They have to be battery power. We're not going to allow electrical devices to be connected to the grid, because that in itself would reduce the reliability of the grid. We decided they had to be edge computing. We didn't want to move a whole lot of data around. We wanted to move just answers about the grid around. We're going to put them on vehicles, and we decided from the very beginning that there'd be no vehicle alteration at all, that the vehicles themselves would be not bothered by a sensor that would be riding along with the vehicles. And we chose the mobile edge computing sensor model because it's so much cheaper than putting sensors everywhere. You need millions of sensors if you put one on every pole in the whole country. So we tried to evaluate the program both from a project, but what if we scaled this up to the whole country? And the antenna had to be designed so it's small enough to fit within the sensor and be completely enclosed. So we used the patented partial discharge discrimination sensor technology that Exactor developed 14 years ago, but it's a PC-based sensor, very heavy computer requirements and power to run it. So it doesn't meet the requirements of that. And we gave that, we know it's very accurate. When we put our sensors in helicopters or cars and drive through or fly over the grid, we can find problems on the grid. And when we go to those points where we believe we detected the source of the emission, we have a ground truth achievement of 99.7%. So it's very accurate, our signature analysis. However, it's very resource dependent. So here's one of the challenges was the antenna I mentioned. The team came up with a quarter wave meandering F-pole antenna that was able to fit within the enclosure of the sensor, which kind of looks like the helmet from a stormtrooper from Star Wars. And that's actually what we used as our inspiration for the sensor design itself. The emission detection to get down to that low power was changed completely. And we went from a PC-based sensor, and the team developed a microcontroller-based sensor that the total parts for this sensor, if you buy just one of them, cost $40. The computer-based sensor that we built cost $4,000. So it's an amazing reduction both in the cost of materials, but also power requirements. And with the new algorithms that were developed at the University of Akron by, yeah, I can't think of her first name, but Miss Desari took the sensor performance to make one measurement from 1 second down to 1/10 of a second. And we take one reading every second as a vehicle is moving. So we can turn everything off for 9/10 of a second and save lots of power that way. Plus the fact we're working now on silicon rather than on a PC-based sensor. So we're down to very low power, very long battery life. The algorithm itself is called mixed error estimation integral, and Ms. Desari developed this for, it's a standardized numerical approach for waveform analysis, but she applied it to our problem. And that was her thesis for her master's degree. And this is just to show you some of the field testing we did. We won't go into, we don't have time to go into it in detail, but it performed as good or better than our $4,000 sensor. So we've had a chance to actually try it in the field. And actually, we were driving through Cuyahoga Falls, and we found an electrical switch that was going to fail. And when we told the electric department about it, when they took it down, it fell apart. And they said, had they operated that switch, it would have failed and blacked out half of the city. So already we've had some commercial success, you might say, with the project. So what we're doing with these sensors, and you see the final packaging design on the right, is we're mounting them on garbage trucks in Akron. 15 garbage trucks drive 5,000 miles every week, and that will give us the data we need for machine learning and repetitive models, and we'll cover the entire city, the whole entire city grid. And with that repetitive data, we're going to develop new algorithms, financial projection algorithms for electric utilities to be able to evaluate the grid, see how it changes throughout the year with all the impacts of weather and environment, and then make financial decisions on what to do with that information. And we're just beginning that deployment. I mentioned we have 5 trucks out right now that they run. You can see their dense area of coverage, and they repeat the exact same route every week. And then we're starting our machine learning on what is it telling us and how can we evaluate the performance of the grid based upon the data we're receiving. So those are just 2 projects of about 8 that we're working on with universities. And it's been such a wonderful experience to work with student teams. And like I said, we've provided jobs, we've provided careers for people, degrees, and patents. And so it's been a wonderful 2-way interaction that we've been so very proud to be part of. And so we've been just so blessed by doing it. So thank you very much.